Hi everyone, welcome to this video where we will discuss the data-free quantization techniques in AIMET. My name is Abhi Khobre. I'm from Qualcomm AI Research. AIMET stands for AI Model Efficiency Toolkit, and AIMET is an open source library brought to you by the Qualcomm Innovation Center. So in this video, we're going to cover the post-training quantization techniques in AIMET, specifically these techniques for cross-layer equalization and bias correction. And together, these are also sometimes referred to as data-free quantization techniques. I hope you have had a chance to look at some of the previous videos in this series, specifically the introduction to AIMET video and also the video on quantization simulation. If you have not had a chance to look at those, I would encourage you to look at those first because they serve as some background to this video. So let's dive in. So in the video on quantization simulation, we looked at two of these use cases before, but let's look at this third use case, which maps well to these techniques that we're going to discuss today. So these techniques for cross-layer equalization and bias correction, they are, we call them post-training quantization techniques, meaning they don't require any fine-tuning. So the way generally this would work is you would take a PyTorch or TensorFlow trained model, you would pass it through AIMET, and for one of the techniques, bias correction, you may perhaps need some unlabeled data sample. So let's look at details why perhaps later on. And then you get back a model, a PyTorch or a TensorFlow model. And now, just without doing much, this model has been made better for quantization. So now if you take this model and take it to run on a quantized runtime, quantized target, you would see better performance, better accuracy essentially. So let's get into the details of what is data-free quantization. So these techniques that we're going to discuss today are explained in this paper, which there is a link for here. The paper is called Data-Free Quantization through Weight Equalization and Bias Correction. This was written by my colleagues Timon Blanker-Wood, Marcus Nagel, Mart Balin, and Max Welling. So in together, what these techniques have, there is a technique called cross-layer scaling and a counterpart technique called high bias fold. And then there is a technique called bias correction. So the flow works as follows. In generally, when models are executed on a runtime, batch norm layers get folded. And this is because batch norm layers are not important or necessary when running for inference. So these get folded into generally into nearby convolutional layers, either a convolutional layer before the batch norm or a convolutional layer after the batch norm. And for this particular technique, what you would do is you would replace the ReLU 6 layers with ReLU, and then apply cross-layer scaling, then apply high bias fold, and then apply bias correction. So this is just a flow, but we will look at details of what these techniques mean. And also, there are very user-friendly APIs to do all of these steps for you in order, so you don't have to necessarily remember the order. So let's go into a little more detail. So batch norm folding is like I explained. You take the batch norm layers and fold it into surrounding layers, generally convolutional layers. And so then you will get a model, starting model had batch norms, and the model that you end up with, the batch norms have disappeared. Replacing ReLU 6 with ReLU is actually fairly trivial. I think most models that use ReLU 6 don't actually, if you replace that ReLU 6 with a ReLU, you would almost see no drop in accuracy at all. But however, there may be some models where you may see a drop in accuracy. And for those models, maybe this is not a appropriate technique. You may replace your ReLU 6 with ReLU and train the model from scratch again, and then perhaps apply this technique. That could be a workaround. Okay, so let's look at this first technique called cross-layer scaling. And what this technique tries to do is it works best on layers where you see, so let's focus on this graph on the left. I'll try to zoom in a little bit more. And while it's kind of hard to read, but let me motivate what this is showing. This is the box plot. The x-axis is just channels in a particular layer, and the y-axis is the range of values within, if you slice the weight tensor of this layer by channel, then the y-axis is the range of tensor values in those slices, right? So it's the min and max of those tensor values. So what this is showing is in this particular layer, which is taken from a MobileNet V2 model and a particular layer in that model, it just so happened that after training, the way the weights have settled is in this particular layer, some of the channels have very little, like very small range, like very, maybe close to 0, -1 to +1, let's say. Whereas there are some other layers which show a large range, like 100 all the way to -50. And so the problem with quantizing a model like this is generally the most runtimes, quantized runtimes, they work on per layer parameters. So you would decide a min max or an encoding for the entire layer. So you are essentially finding out encodings across all these channels, one single encoding. And you can see that this can cause a problem because you would either be able to optimize for these cases where you have a large range, but then you would lose out accuracy on all these other channels. Essentially, these would almost go down to 0, like you're just throwing those out. On the other hand, you could try to keep the range very, very tight, and then it would benefit these channels, but it would very adversely affect the channels that have larger range because they would all get clamped to the small min max. So this is a classic problem, and it's seen in certain models. Specifically, we have seen these in like the MobileNet family of models. And as a result, what happens is, certain models, and it all depends on how you train the model and where it settles. So some models show a very sharp drop in accuracy. Some versions of MobileNet V2, let's say, show a very sharp drop in accuracy when you run on quantized targets. So what this technique will do is it's doing the following. It's taking, on a per channel basis, it's trying to see the range, and it's looking at the amplitude across the channels, and it's applying like a scaling factor to reduce the range on one channel of a layer, and that channel directly maps to the input channel on a subsequent layer. So let's say this was a convolutional layer and this is a convolutional layer following it. You can take this, you can scale down this particular channel by a factor, a scaling factor, and you could scale up the corresponding input channel on the next layer by the same factor. And mathematically, you would result in the same computation at the end of the second layer. On the other hand, what you have done is you have like reduced the range of this channel. So we find these kind of scaling factors on a per channel basis, and then equalize the channel. So what the result of all of this would be that you would get something like this. So if you notice on the y-axis, the range has been reduced dramatically. It's gone from like -50 to 100 to -0.75 to 0.75. So now across all the channels, you have very good resolution, and this is going to do pretty well on quantized accuracy. So when we do this operation of cross-layer scaling, not only are we scaling the weights here, the channels in the weights, but we are also applying the scale to the bias as well. And this can sometimes result in very high biases for these layers. And so there is a secondary technique that you apply. If you apply cross-layer scaling, you apply this high bias absorption or high bias fold technique. And what it does is it basically, again, looks at the high biases or high amplitudes of biases per channel in a particular layer and simply scales the weights of the next layer, the subsequent layer, to account for some of these high biases. So you scale down the bias and you scale up the weights of the next layer. So these together, these two techniques, cross-layer scaling and high bias fold, are we refer to as cross-layer equalization. And a sort of a technique that is not related to cross-layer equalization, but actually in practice seems to work well when applied after cross-layer equalization, is called bias correction. And so in this technique, let me motivate through this example maybe. So in this technique, what we would do is, so the motivation for the technique is that if you quantize the weights or parameters of a particular layer, it seems to show, empirically, it shows a shift in the outputs of that particular layer. So if you quantize this layer, convolutional layer, it will show like a shift in values, like a shift either in the positive direction or the negative direction. And the paper explains the why, what is the rationale for this shift, but this is what is observed. So what this technique does is it simply, in one case, what you could do is you could send some data through a quantized model where you have quantized the parameters. You can take a reference model, which is just in floating point, and you could observe the outputs of this reference model and observe the outputs of the quantized model and figure out this shift. And once you have figured out the shift, you can correct it because we have this parameter called bias. And so that exactly is something that gets added to the output of that layer. So you can use the layer bias to just simply correct this. So this technique is called bias correction. And there are two kind of variants of this technique. I think where most often we use this empirical bias correction technique where we send some samples through this model. But if you had batch norm layers in the model, then we could use the batch norm statistics as a sort of a placeholder for the data that, or the observations that you would make if you pass data. So instead of passing data, you could not pass any data, just use the batch norm statistics and infer the correction based on those. So so this explains these two techniques. So let's go into a code example and then we can look at some more details. Thank you. Okay, so we'll start with a clean editor session here, and then let's start with some imports. And let me explain, what these imports are. So, we have built-in techniques for doing batch norm folding. So there are imports for that. There is this is the API we are going to use for doing cross-layer equalization, and then bias correction. And then we have our standard pipelines that we have seen in the other videos for evaluation and getting data loaders and so on. And also there are some helper utilities to visualize. So there are some visualizations tools baked into AIMET, and there are some utilities for visualizing. Okay, so let's start with a model. And in this case, we are going to use a trained MobileNet V2 model. I think in the previous videos, we have been using a ResNet 18 model from Torch Vision, but for this particular video we'll use MobileNet V2, and the reason for that is ResNet models, as we saw in the quantization simulation video, are fairly robust to quantization. So I think it's not going to make the case for you in terms of what these techniques can do. Okay, so I got a model, MobileNet V2 model pre-trained. And it's using the standard ImageNet data loaders here. So that's the input shape of the model. And then we are simply going to evaluate the model using our pipeline. So we'll get a floating point accuracy. And then what I'm going to do first is I'm going to motivate the problem for you. Okay, so what we would do is we would first try to fold the batch norms. So what we use the API to fold the batch norms. So I'm going to create a copy of this model because, you know, this is a problem statement. I'm going to create a problem and then I don't really care for the problem model, and then we will correct the problem. So I created a copy of the model and then I just basically made one single call, fold all batch norms. You pass it this model and pass it the input shape, and it essentially changes this model in place and the batch norms are gone. So we can take a look at the model after this is done. But before we do that, let's also use some of our visualization techniques. And so let me get some more code over here. So we are going to make use of this call, and we'll look at some more details of this later on, but essentially we're going to visualize one specific layer in this model, features 1.con.0. And this particular layer is one of those problematic layers that I had shown you in the user guide picture before. There are multiple such layers. Not all layers would show that problem, but some layers do, and those layers have a outsized effect on the drop in accuracy of the model. So, and then finally, to motivate the problem as well, let's try to now get a quantized accuracy of this model. So we had the floating point accuracy over here. We are going to get quantized accuracy. So what this code would do is do what we saw in the quantization simulation video. It's going to basically create a quantization sim model and then evaluate the model, right? So it's just simply doing that. Could probably make this a little bigger. I should have realized that before. Okay, so let's run up till this point. So the batch norm folding is going to take like 1 or 2 seconds. This evaluation takes around like 9 to 10 seconds. The quantized accuracy, to actually create the simulated quantized accuracy, takes a little bit of time, a few minutes, like on the order of 5 minutes here. So I'm gonna let this run, and I will pause the video and resume when it's finished. Okay, welcome back. I think this run is finished. So if you remember, let's recap. We calculated first the floating point accuracy of the model, and then we folded the batch norms and then calculated quantized accuracy of the model. And so if we look at the results now, you will see that the floating point accuracy came to, for this particular model, 72.65%. And then the quantized accuracy actually was a very, very low number, like 0.1%. And so why is that? And to take a look at this, let's look at that visualization that we had done over here. So the visualization looks something like this. On the x-axis is the channels, on the y-axis is the range. So you would, and this is for a particular layer, right? Remember we chose to visualize this features.1.con.0. And this is just to illustrate. I think there are some other layers that show similar behavior in this model, and there are other layers which are perfectly fine. But this layer is one of the problematic layers. So as you'll see, like if you look at the different channels, some channels have very small range. Like in this case, the range is -1.24 to 1.69. So it is, totally about 3, right? Absolute 3. Whereas if you look at this channel over here, right, this particular channel, that's channel number, let's say 29, that has a range of -57 to 94. So that has almost like 150 absolute range. So the problem with something like this is, like, if you chose to account for these kind of big values in this particular channel, then you would choose your min max as something in that order, right, from let's say 100 to -50 or something like that. And if you did that, then these other channels which have very low range, they are going to get completely destroyed. These channels will simply all of the numbers in that channel will essentially boil down to one or two numbers, right? So in other words, we are throwing away the channel. And the same way, vice versa, if you chose the range to be very low, then these channels are good, but then the other channels which have the large range, they have a big, essentially you're clipping all of their values, right? So most of their values will get clipped. And so this is the problem. So now we need to solve the problem. So let's go back to the code. Okay. So now I'm going to, in this code, try to solve the problem. And I'm going to use this Equalized Model API that we had seen, right? This API is actually fairly very easy to use. So you just give it the model that you want to equalize, and you give it the input shape of the data that feeds into the model. And just this one call is going to actually equalize all of the layers in place. The way we can know what it has done is to do another evaluation. So let me bring forth some code for that. Okay, so let's go here. So essentially we'll get another quantized eval accuracy, and then we'll visualize it afterwards, the same layer again. And now to make this run a little faster, what I'm going to do is we already know the floating point accuracy. So it was 72 something. Maybe I'll leave the floating point accuracy, but let me remove this. Let me comment out this part so that we know that this accuracy was 0.1%. So it'll just make this run be a little faster. So let me run this, and I will pause the video and see you in a few minutes. Okay. So welcome back. So this run is finished, and you see that after doing that equalized model call, the accuracy has recovered nicely back to 70.15. And let's take a look at the visualization just to see why that is so. So what this is showing is the solid lines here are showing the exact same curve from before. So some channels have less range, and other channels have high range. But there are these dotted lines in the middle, and these are the ranges after equalization, and you can see that the ranges have become very narrow, and so that's the reason why it helps with quantization, because it's very easy to quantize across all these channels when the range across the channels is very tight or almost the same. Whereas if there is a large variation in range across channels, then it is very difficult to quantize that layer. Okay, so let's go back to the code, and let's see what else can we do, right? So we started with 72.6 and we ended now with 70.15. So it has come quite a long ways from 0.1, but still a little ways away. So the next technique we can apply is a thing called bias correction. And with this bias correction technique, once you apply that, you're going to see that the accuracy recovers close to what the floating point accuracy was, within 1% or so. And let's take a look at some of the parameters in here. So as we know from bias correction, we use like a quantized model and a reference model floating point, and we observe outputs of layers. So to observe outputs of layers, we have to feed some data into the layers. So from the correct bias API, we have to specify how many samples that we want to use for this passing through the model. Generally, samples on the order of 500 are good enough. And then since we do quantization, we have to send some quantization parameters. These are very similar to the parameters we saw when building the quantization sim model. So, the quant scheme, TF or TF enhanced, rounding mode, and bit widths for activations and weights. And that's it. So let's now, I'm not gonna actually run this because this will take a little while to run, But the other thing I wanted to share with you is the API docs for TensorFlow, because all through this effort, we've been fairly looking at the PyTorch APIs. And the PyTorch APIs, for example, for cross-layer equalization, they show, like here's the equalized model input shapes. We saw this call. There are no additional parameters here to specify. It's a very simple call from a user perspective, and it does a lot of things automatically under the hood. And the code example we looked at is very simple. You have a model and you just call equalized model. So if you look in the TensorFlow side, APIs are actually very, very similar. So again, equalized model, instead of a model, you take a TensorFlow session. Instead of taking input shapes to create random tensors to pass through the model, we have the starting ops and the ending ops, or starting ops and output ops, names of the ops. And that will allow us to sort of know the starting point of the graph that we should look at and the ending point of the graph. And so here is an example. For example, we take ResNet 50 from Keras, TensorFlow Keras, and we get the session and the graph corresponding to it. Here we are creating like an empty session, but I think this is just for illustration purposes. I think when you load your model, you would load it into a regular session. So you pass that session into the equalized model call and you'll get back a new session. Okay, so essentially the call is between PyTorch and TensorFlow are very, very similar and fairly simple to use. So I think that's all I wanted to cover today. I hope this has been useful to you. These data-free quantization techniques are actually, very, very powerful and do a pretty good job at like quantizing, models that used to be difficult to quantize, like MobileNet V2, and they do a pretty good job with those. And I hope this video was useful for you. If you have not checked out the other videos in this series, I would encourage you to please go and check those out. And thank you. Bye.